a strange pair of giant planets orbiting a young sun-like star. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. Back in 2020, astronomers used the Very Large Telescope in Chile to capture an image of not one, but two giant exoplanets orbiting a young sun-like star. The system was called YSES-1. It was the first time that we'd ever directly imaged a multi-planet system going around a star that was much like our own. Now, thanks to new observations from the James Webb Space Telescope, we're getting a far deeper understanding of these worlds. One of them is still surrounded by a dusty circumplanetary disk, and the other has silicate clouds in its upper atmosphere. To tell us more about these worlds, I'm joined by two members of the research team behind these discoveries, Kielan Hoch and Emily Rickman from the Space Telescope Scientist Institute. We'll explore what this young planetary system can teach us about how planets form and what separates gas giants from brown dwarfs. Once more, JWST is redefining what we thought we knew about planetary evolution. Then we'll be joined by Bruce Betts, our chief scientist for What's Up. We'll talk a bit about why it was possible to directly image these worlds in the first place, and what it would take to directly image older, colder worlds with missions like the upcoming Habitable Worlds Observatory. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. Before we jump into today's story, a quick heads up. The Planetary Society is hiring. We're looking for a systems assistant to help support our IT operations. This is a hybrid role based in Pasadena, California. It's ideal for someone who's early in their IT career. We're looking for someone who's passionate about learning, problem solving, and growing in systems administration, user support, and cybersecurity. To apply, send your resume and cover letter to systemsassistant@planetary.org by September 15th, or visit planetary.org/careers to learn more. Now on to our main story for today. The YSES-1 system is one of the most intriguing exoplanetary systems that we've ever directly imaged, and until just a few years ago, we didn't even know it existed. In 2020, astronomers using the European Southern Observatory's Very Large Telescope in Chile made a remarkable discovery. Two massive gas giant exoplanets orbiting a young sun-like star about 310 light-years away in the southern constellation of Musca. It was part of the Young Suns Exoplanet Survey, or YSES, which is where the system gets its name. YSES-1 is only 16 million years old, basically a cosmic toddler compared to our own sun, which is about 4.6 billion years old. The VLT's image of this system is absolutely beautiful, and I'm going to be sharing it on the webpage for this episode. It was humanity's first directly imaged multi-planet system around a sun-like star. Both of these worlds, YSES-1b and YSES-1c, are enormous. The inner planet, 1b, is about 14 times the mass of Jupiter and sits about 160 astronomical units, or the distance between Earth and the Sun, from its star. The outer world, YSES-1c, is about 6 times as massive as Jupiter, so not as big, but orbits even further away at 320 AU. The scale of the system all by itself would be interesting, but thanks to follow-up observations from the James Webb Space Telescope, it's even more exciting. In a paper published in Nature titled Silicate Clouds and a Circumplanetary Disk in the YSES Exoplanet System, a team of early career researchers revealed that these two exoplanets appear dramatically different. YSES-1b is still wrapped in a dusty circumplanetary disk with signs of olivine dust grains. That's surprising because those disks are thought to dissipate within 2 to 5 million years after they form. At 16 million years old, this one might be forming moons or might be regenerated by collisions. YSES-1c, on the other hand, has silicate clouds suspended high in its atmosphere. Based on the temperature of that world, those clouds shouldn't still be there, or at least that's what some of our models suggest. Similar objects like brown dwarfs typically shed those clouds at this stage. This is the first direct detection of silicate clouds on an exoplanet orbiting a sun-like star, and it raises major questions about how atmospheres evolve in young gas giants. To walk us through what these discoveries mean, I'm joined by two of the scientists behind the study, Dr. Kielan Hoch is a Giacconi Fellow at the Space Telescope Scientist Institute and was the principal investigator on this JWST Cycle 1 program. She submitted this proposal when she was still a graduate student. And Dr. Emily Rickman is a science operations scientist for the European Space Agency and also works at the Space Telescope Science Institute. She's a project-level member of the JWST Telescope Scientist Team for coronagraphy. We'll talk about what it was like to observe such a rare planetary system and how these findings challenge current models of planet and moon formation. Thanks for joining me on Planetary Radio.
Happy to be here.
Pleasure to join. This is such a cool story. I mean, not only are we talking about a system where we've gotten to actually observe multiple planets around a sun-like star, directly imaging them, but now we're learning some really interesting things about these worlds that kind of completely broke our expectations. But before we get into the actual science of this thing, I wanted to learn a little bit more about you guys. So, Kielan, you've been working on the system since its original sphere discovery in 2020, and now you're the lead author on this new JWST study. What was it like to be able to revisit this system and actually dive into what's going on with these worlds?
It was an interesting time. I was a grad student I was in my last year of grad school, trying to get ready to defend my thesis. And I was working with my co-PhD advisor, Dr. Marshall Perrin at the Institute, and we were trying to figure out how to use the near-spec instrument on JWST to look at exoplanets, because it was originally designed to look at faint, puffy galaxies. At the time, we didn't necessarily have a working simulation way to simulate what the data would actually look like, but we knew the field of view and we knew some other things about it. So we made our own simulations. And the system was discovered in 2020. It is the lowest mass host star to host two directly imaged exoplanets. And it is a young solar analog. So it's about the same mass as the sun and is also a G-type star, but 16 million years old compared to our sun being 4.5 billion years old. So it's a very young system. And when it was discovered, it was actually after the time that the early release science and guaranteed time observations had to pick their targets. So we got kind of lucky because it would be a very good target for those programs. So once we kind of started running some simulations to see if we could look at the system with near spec, even before JWST launched, we realized that we could actually get both planets in the same field of view. So essentially looking at these objects two for the price of one. So that's what the entire proposal was born on or born from in a way. And then we added in the MIRI observations when we added some atmospheric modelers to our proposal because they were interested in clouds. So we're very happy we did that because that was one of the major discoveries. But then you have the JWST launch, and we got the proposal feedback back, and we found out that we had actually been awarded the time. And so it was a cycle 1 program. So it was in that first cycle of data that we got from the telescope. And it took until, what year is it? 2025, essentially, to get this published, because when the data were coming down for the first time, the science calibration pipeline was brand new. So we didn't really know, we can't plan for every little tiny intricacy that can happen after you launch something into space and turn all the instruments on. So it took a very long time to reduce the data to see the spectra of the objects or what could be in their atmospheres, in addition to helping the calibration team improve the pipeline basically as we're going through this program. And as we did that is when we started to make some of the discoveries. And it was really cool, especially with the outermost planet, YSES-1c, because it is so faint at the time, it was nearly impossible to get spectra from the ground of that object. So it was the first time we were seeing spectra of the outermost planet entirely. And we actually thought the innermost planet might be kind of not boring, but that we kind of a more familiar object. And that ended up being a very weird and interesting object, which is the story of most JWST programs and papers that are coming out nowadays.
Really, though, these exoplanets have always thrown us for a loop when we learn more. But the amount of information we can glean from these worlds from JWST has just opened up a whole new realm with these worlds. And I'm glad that we got a closer look because, I mean, I wouldn't have guessed that thing had a ring on it. It's so cool. But Emily, you focus mainly on exoplanet atmospheres and high contrast imaging. How did you end up working on this project?
Yeah, so it was a really exciting time for me because I had just joined STS back in mid-2020. And I joined initially as a fellow for the European Space Agency, so ESA. And it was when I first met Kielan and we started talking about Cycle 1 JWST proposals. And it was just so exciting to become part of this really incredible team of people. There's a lot of expertise here at STScI and become involved in what was going on and brainstorm all of these amazing ideas. And it was suddenly becoming very real that JWST would launch imminently, thanks to the creativity as well as the technical expertise of Kielan and others in the team that this idea kind of came about. And I was really excited to be there for sort of the birth of the idea in a way. I think I even remember the initial meeting that we had on this. We used to have a Friday afternoon co-working hour where we would kind of brainstorm JWST proposal ideas and what things we wanted to focus on. And this was really my first introduction to true JWST science. And I was very fortunate to arrive at the Institute just sort of 6 months before launch. I really couldn't have timed it much better if I tried. And so that's how we ended up working together. It's how I ended up being on the program and sort of providing my input and hopefully some expertise into the program and ultimately the paper.
Well, she made sure that we had the telescope pointing in the right spot. So
yes. So I do a lot of orbit fitting and astrometry, so understanding planets relative to their host stars and things like this. And some of the complications when we set up these observations is making sure that we don't accidentally put the planet underneath a bright diffraction spike of the star, or that we don't end up on a part of the detector that would be flooded with a lot of the bright starlight. And so doing the coordinates for these things can be quite complicated. And I was lucky to be able to help out with components of that. Yeah, so that's one of the things we have to think about a lot when we do this kind of science, and to get data that is usable and as beautiful as the data has been. So yeah, it took a lot of discussion with many different people. It's certainly not just from me, but it's also an aspect of the science that I work on as well.
I think it's an aspect that a lot of people don't think a lot about as well, right? Thinking about where's that diffraction spike going to be? Or if you're using an older telescope, which column of pixels in this CCD is burnt out because someone pointed it at the wrong thing? There's a lot of nitty-gritty things here that I think people don't really know about. They just assume it kind of works.
Yes, and we have to work in many different coordinate systems as well. So people might be interested to know we have the coordinate system of the telescope itself, and then each detector has its own coordinate system because each detector sits in a slightly different orientation or direction with respect to the telescope itself. And then we have obviously sky coordinates. So when you look at an image of the sky, that also has coordinates associated with it. So trying to transform between those different coordinates and how they interplay with one another can also be quite an intricate problem to solve.
Yeah, that's a lot of math. But thankfully, it all turned out, right? And as you said earlier, this system wasn't discovered by JWST. It was discovered by the European Southern Observatory. But what was that process like? And what is this Young Suns Exoplanet Survey?
The Young Suns Exoplanet Survey, we call it YSES for short. Mm-hmm. Part of what JWST has been so good at doing is following up a lot of these ground-based observations. And so actually my background was predominantly in ground-based observations. I worked with SPHERE data a lot. So SPHERE on the VLT, which is the imager responsible for finding YSES-1 B and C that we now see in this system with JWST. And so, yeah, it was kind of nice to come in as well with the SPHERE expertise hat on and say okay, I haven't really worked with space data before, and sort of how can we push out to those longer wavelengths that we just really can't access easily from the ground, because you get a lot of thermal emission from the ground at those wavelengths that JWST is observing in. So yeah, neither of us were part of the YSES-1 original survey, but actually the first author of that study has since left academia. he was a grad student of the discovery. This is Alex Bohm 2020 paper who discovered it. But Matt Kenworthy, who is based at Leiden University, who was student supervisor at the time, is involved in this program and was very happy that someone was following it up and looking at this system. So I think it's just been very exciting to bring all of that data together and to kind of have this continuation of the story of what was already a very exciting discovery, and to amplify that excitement through the use of JWST.
I mean, especially with these kinds of younger systems, who knows what debris and dust might be in the way. The capabilities of something like JWST and that specific kind of, mid-infrared range that it can actually peer into is really pivotal here. But I think there's another layer, especially with the direct imaging, which is that because it's such a young system, this actually contributes to how we're actually able to directly image the system. Which, I think it's already so challenging to try to take images of these worlds. And these ones aren't particularly close to their star, right? They're pretty far away. So you'd think maybe they don't get enough light for us to see them. How did that age of the system play into this?
So direct imaging in general, we tend to be more sensitive to younger systems because as your object is forming and collapsing, it's heating up on the inside. And so what we're actually detecting is that thermal heat coming from the object kind of forming and collapsing down, going through the atmosphere to our detectors. So it's that thermal light that we're able to see. So therefore, if we block out the host star light, like they did in the discovery paper using a coronagraph, you hope that you'll be able to see a bright thing somewhere close by or kind of off to the side. And the main reason we're able to see that is because they're all still hot from forming. And planet formation takes a very long time. So,
yeah. And planets, unlike stars that don't fuse in their cores, just continue to cool over time. And as they cool, they are not as bright anymore. We don't get as much emission from them. And so, as Kielan says, when they're in those formation stages, they're really at their brightest, most ample opportunity to get the most amount of photons, to get more favorable contrast that we're able to directly image these things. And then as these systems get older, it becomes increasingly difficult as the contrast ratio between the planet and the host star increases and becomes more difficult to do.
A little easier with younger, smaller stars compared to giant ones. But even then, super, super challenging. So I'm hoping that inevitably, at some point, who knows when it's going to happen, we actually get things like the Habitable Worlds Observatory and other things that are going to be trying to do more of these direct imagings. But in the meantime, I mean, it's wild that we got this at all. But then we looked more into these worlds and it got even stranger. In your paper, you mentioned that these planets formed in a similar environment, but now they're very, very different. How does that help us probe some of our planetary formation theories?
So it's challenging them, right? You have essentially two main theories. You have the core accretion theory, where you have your protoplanetary disk around your forming star, and it would accrete all of the heavier elements, so a core essentially, and then an atmosphere afterwards. And then you have the other theory, which is disk instability, where essentially rather than having all the heavy things collapse in first, everything kind of collapses evenly. And so you get more of a Jupiter gaseous object. And the formation theories do have ideas on, if it formed at this point in the disk, then the CO in the disk would be ice at this area and blah, blah, blah. So there are ways that we're trying to test where the thing may be formed and maybe how did it form based on the differentiation of all of the material as it collapses down to make the planet. But what we're seeing here is that those theories are probably a little too simple. These objects are so widely separated that we're not sure necessarily even where that disk could have been. How did they get scattered out there? And then, why are they so insanely different at these separations? And most of the things that we're starting to see with JWST data is that most of our theories are wrong or just need to be improved, or there's a lot more missing knowledge than we previously thought. Especially with the innermost planet, we discovered the disk around it, But usually the circumplanetary disk, so like disk around the forming planet, should not still be around at 16 million years, which is the age of the system. Usually they live about like a couple million years and then they collapse in onto the planet or disperse. So seeing that we still have a lot of material around the planet starts to complicate even most planet formation theories. And then the detection of olivine, so these really hot, small dust particles as well, you would only expect them to be in a super, super young object that's forming like less than a million years old. And so now that we're seeing that in a system and in an object that's 16 million years old, why are those fine grains still there? That's where we bring up the question of, could there be a moon forming and causing collisions to cause all of these grains to become small and hot again, like it's a second generation disk? But that complicates the time scale of most of the theories we had from the ground-based data, at least.
Yeah, it makes me think about a lot of the more recent discourse about the age of Saturn's rings and how, they're a lot younger than people thought they would be. I think when I've been talking with people about these stories, people generally just assume like, hey, that planet has rings and they stick around forever. But really, though, we're time limited in seeing these kinds of things. So it's really fascinating that we're seeing it at this point. But this leads me to another question, which is we keep saying that the system is about 16 million years old, but how do we know that? How are we ballparking that?
So usually for aging stars, you look at the cluster of stars themselves to try and age the whole kind of little star forming region. So you just imagine that if you're able to age one of them or two of them, like the whole system itself is probably going to be around that age. But this can change because there's many different ways to measure the ages of some of these stars.
And this particular, is it a cluster or an association that this star is in?
It's in Upper Scosen.
Upper Scosen association, part of the actual survey, the YSES survey, the Young Suns Exoplanet Survey, was targeting stars particularly in this association. So it was kind of intentional that the stars they were looking at were all of the order of the same age as well.
This first planet, the inner planet YSES-1b, and just for people who are listening who are new to kind of exoplanets, we always call the first exoplanet in a system by B, not A. I know that confuses a bunch of people, but this one is actually, it's pretty big. It's about 14 Jupiter masses. So it's really kind of interesting to think of a world at this size that still has these ring systems. You spoke a little bit about this, that perhaps there are moons forming and that kind of thing, but like, what is the full scope of possible reasons why these rings could exist?
Endless reasons at this point. I mean, the only real system that we're able to look at and go send things to is our own solar system. And humanity has not been alive very long, right? So we're looking at a lot of these systems at various stages of millions to billions of years, and a lot can happen in that amount of time. So we have a small sample size, our own solar system, and then maybe catching some other system in a very special time. But all we have to go on is essentially we come back to our own solar system. And so the reason why I attribute in the paper that these fine grains are probably second generation and probably from collisions is because those grains, olivine grains, are essentially what in the solar system and planetary field call chondrules. So those are olivine grains that they find in meteorites that they trace back to our own protoplanetary disk, essentially, when you're forming these moons and planets and things like that. And it comes from collisions. There are a couple other things that the small olivine grains could come from, but they're more high energy, high energetic processes. And with something that's 14 Jupiter masses that is much smaller, if you deduce from all of the things that would cause those chondrules to be in our protoplanetary disk around our sun, it makes more sense that it would be collisions or the formation of a moon. Unfortunately, there's not much we can do in terms of trying to determine whether it's one or the other. People have had some papers out that are attempting to look for moons around some of these giant exoplanets with RV data, so radial velocity data, seeing if there might be something tugging on the planet. But you need a very special instrument to do that. And again, these objects are faint, they're close to their host star. And because the system's really young, the host star itself had high activity. So to be determined if we're able to tell if there's moons around there, but that's kind of the status of things, I would say. It's a lot of I don't know and a lot of we need to keep pushing forward.
Yeah, I think that emphasizes the nature of what we do. At the end of the day, we're looking at very dynamic environments and we're taking a snapshot of that. And our understanding can only build on the basis of the things that we've already observed or see, for example, in our own solar system. And then we get this bit of a frog hopping effect where we take observations and then we come up with some theories to explain what we see, and then we take more observations and that might challenge our theory and so forth. And so I think we're really at like an exponential stage of that with JWST, because we're opening up this huge avenue of wavelength range, this huge scope of wavelength range that we haven't previously been able to look at, and this level of detail and sensitivity. And I think we're at that stage where we have these beautiful observations, but we sort of need the theory to catch up a little bit to truly understand the challenges that we've now presented to those existing theories. And I think that's just, really how we unfold and start answering some of these exciting questions that we have in astrophysics.
Yeah. I was recently at an event that was dedicated to all exoplanet stuff, and many of the people there were just vaguely interested in exoplanets and were really shocked to learn that we've discovered almost 6,000 of these objects, at least confirmed. But that being said, that doesn't mean that we know a lot about worlds going around sun-like stars. Preferentially, we're finding these things through transits that are going in front of large stars or large planets themselves. So there's kind of like a skewing in the amount of information that we can actually learn about these systems. So it's really cool and makes absolute sense that we're going to be completely shocked by what we find as we delve deeper into these like smaller worlds.
Absolutely. Yeah.
YSES-1c is actually, I think, the more shocking situation here. I mean, finding a ring around a world, we expect this to happen when there are collisions, especially when things are forming. But this thing is so weird. You found these silicate clouds in the atmosphere. Why is that such a big deal?
It's a big deal because these directly imaged exoplanets tend to be about a Jupiter size or a bit larger. So they're large gaseous planets because it's detection bias. Those are the ones that we can see. The easiest comparison we have to these objects that are really hard to observe are isolated brown dwarfs. So some people call them failed stars, but I obviously think they're cool stars. So we compare a lot of our exoplanet spectra or data to brown dwarfs because we're able to observe them much easier and the data that we get from them are way cleaner. But something started to happen in the early to like 2010s, I would say, where they were comparing these spectra of brown dwarfs around the same temperature and surface gravity that we imagine for our exoplanets. But the brown dwarfs their spectra weren't impacted by clouds. But then if you looked at a directly imaged exoplanet spectra that was around the same temperature, the spectra was impacted by clouds. So there started to be this divide in do these exoplanets of a similar mass that have formed around a star, they seem to have different clouds than objects that formed isolated, like in a cloud, molecular cloud, that just got lucky enough to like start to turn on, that gravitational collapse. And we have a treasure trove of data of isolated brown dwarfs with the Spitzer telescope. And illustrating this silicate absorption and silicate clouds that you actually can detect and see in a lot of these isolated brown dwarfs. And the shocking thing about this observation, and honestly about VHS 1256, is seeing it in an object that is around a solar type star, but also the shape of the feature is entirely different than any of the isolated brown dwarfs and VHS 1256b. So VHS 1256b is, I would say, more of a planetary mass companion because we're still not entirely sure how it formed. The system that it is orbiting around is a low mass M dwarf binary system, and it is widely separated. And a lot of theories, and I think I even have a paper on this back when I was in grad school, that the object most likely formed at the same time as the central binary system. And when Brittany Miles' paper came out from the early release science program that Emily and I were both a part of, it was the first direct detection of silicate clouds in a companion, but that silicate absorption looked very similar to the ones that you would see in the isolated brown dwarfs. So then when we thought to plot our silicate absorption feature against all of those, it was shifted almost like a full micron from the start of the other isolated brown dwarfs and VHS that we've looked at with James Webb. And so that kind of aligns with some of the theories we had before about maybe these directly imaged companions, like maybe they did form in some sort of special way that gives them, that is like impacts their atmosphere to cause the clouds to be different and look different. So this is one data point in that, I would say. So I don't want to claim like, oh, this is the like beginning of this new class of clouds and possibly a new formation tracer. We have to really keep looking at these directly imaged companions to keep plotting and noticing if there are these same like shifts that we see in something around a big star versus something around like in, a really small system or just an isolated brown dwarf. So this could be the start of a whole new class of clouds, or this object can be a complete anomaly. But that's kind of the state of affairs, I would say, with this object.
We'll be right back with the rest of my interview with Kielan Hoch and Emily Rickman after this short break.
This October, NASA needs you. Hi, I'm Jack Corelli, Director of Government Relations at the Planetary Society. In response to unprecedented proposed budget cuts to NASA's science programs, the Planetary Society and a coalition of our allies and partners are organizing a special day of action to save NASA science. Join us in person on October 5th and 6th in Washington, D.C. You'll receive training on effective advocacy from our team of space policy experts. Then head to the Hill to meet directly with your representatives in Congress to advocate for protecting NASA's science budget and ongoing missions. If you can't come to Washington, D.C., you can still pledge to take action online. We'll give you the resources you need to be part of the movement to save NASA science. This event is open to any U.S. resident, no experience required. Space science benefits all of humanity. Let's stand together to protect it. Registration is open now at planetary.org/day of action. We'll see you in Washington.
As we said, the system is fairly young and these worlds are pretty warm. But at these temperatures, most of these models predict these clouds would dissipate. Why would we normally think that they would sink or disappear at those temperatures?
I would say it's based on observations of like isolated brown dwarfs. Because we have something in astronomy called spectral typing, which some people have opinions on it. But like back then, we didn't necessarily have 1D atmosphere models. So all we had were spectra of these like really nice spectra of a lot of these isolated brown dwarfs. And so people would plot them and look at the differences that they see in like the slope and the features and things like that, and then would classify them in different types of in different spectral types, essentially based on some of those changes. And what you start to see, at least in like the T dwarf range, where you have about like 900, 800 to 1,000 Kelvin type brown dwarfs, their spectra distinctly look like there's no clouds in them from at least that wavelength range. And then as you go down to these L-type brown dwarfs, you do start to see clouds being a more important thing. But when you are looking at the T dwarf temperatures, which line up with a lot of directly imaged temperatures, and you're looking at their spectra, like a spectra that we believe is not impacted by clouds, and then you look at this spectra that's supposed to be the same temperature, you can see it has those weird cloud impacts like you would from the L-type brown dwarfs. And so in addition to that and all of the 1D modeling that a lot of modelers have been able to do, they have determined that, oh, well, in a perfect brown dwarf with like this perfect type of convection with these specific equations, right? Like it's all just assumptions, like this is what should happen. So they should fall below the photosphere of what we're seeing. We are still struggling to figure that out for the exoplanets.
Yeah, so I think it kind of feeds into the point I made before of like observations being taken, theory somewhat trying to catch up with that, and the cycle continues. And that's a really, beautiful explanation that you just gave. And ultimately, like the brown dwarf sequence that we have is kind of like an evolutionary sequence in a way, but it is, as Kielan already mentioned, based off of like observations and trying to kind of spectral type things. But from a physical perspective of trying to explain that, as you kind of go down the sequence in terms of as you get cooler and cooler, you essentially get molecules in the atmospheres of those brown dwarfs that start to sort of condense out, and you start to lose clouds as you go to those cooler and cooler temperatures. And that typically correlates with age. So you have colder objects as you get older, but there is some dependence there on things like their formation, like when they formed, how massive they were, and things like that. So it's a little bit more intricate. Yeah, so there are many different axes at play, and trying to observationally group them together and then take the theory to explain why we see it in that way. And those things kind of go hand in hand.
Kind of terrifying to think, though, that there are just these worlds out there with these silicate clouds are just, I don't know, raining shards down onto the inner part of the planet. Not like we think things would be living there, but man, that's just terrifying.
Yeah. And then another interesting thing is the silicate clouds. We see them here directly. Some transit spectra and objects with JWST have some detections of clouds, of silicate clouds as well. But there's like also this other parameter and dimension in terms of how the silicates themselves are connected. And so the two primary silicate types that we use are crystalline or amorphous. And so because JWST is so good with the SNR and with MIRI, we're able to get, at least with direct imaging, we're able to actually see possibly other substructures in this absorption feature, rather than it just being like, oh, like we know this has to be a silicate cloud because there's a dip right here. You start to see some structure there. And some work I'm really excited about by Dr. Sarah Moran, who is over on the East Coast now. She has a new paper out called Neglected Polymorphs, which I think is a fun paper title, but her whole work is about there's a ton of other ways you can connect silicate particles together, such as polymorphs, and there's different shapes you can make. And her work in the lab has shown that you can actually stack some of these intricate polymorphs in a certain way that you can get the same type of smoothed out feature that you would expect from amorphous and things like that. So we may not even have the right structure of silicates because we haven't really explored that parameter, and because we haven't had the exquisite data that we do now. So that's also another thing about this feature and about kind of having these models and things catch up, is that we're only considering these two simple things that we've always done. And now we're starting to learn like there's this whole other realm that we now have to take lab data of. So we have proper opacities, essentially like where these dips should be and what the shape should look like in the mid-infrared, which we never had before, never had a real reason to, but now we do. So now we're waiting on new lab data. We're also waiting on like models and atmospheric models to try and figure out how we can fit this data better. One of our first observations in my paper that was out, I think 2024, we looked at a brown dwarf. It was the first high contrast observations with the near spec IFU, kind of to prove that we could look at something really bright, or like a really bright host star and a really faint companion with the near spec IFU, since the IFU itself does not have anything to block out the starlight. So we're trying to look at these things without even like something to block out the host star. And in that observation, we were able to actually pull out the brown dwarf companion, pull out the signal, and we got this exquisite spectra. But when we tried to model that spectra, there's a chemical process called disequilibrium chemistry. And so it just means that there's more complex things happening as all these molecules are churning in the atmosphere. And what we found out was that essentially a lot of our disequilibrium chemistry models did not include CO2, carbon dioxide. Most of them included carbon monoxide, methane, and water, but none of them had CO2. And what we learned is that CO2 is actually very important to consider in disequilibrium chemistry. And now a lot of atmospheric model grids now include CO2 in their disequilibrium chemistry and had updated all of their model grids for that. So that's just another example of like the data driving, oh, we got to go fix this, like challenging the models and constantly improving our knowledge.
It's got to be such a fun job to try to figure out what's inside of those spectra. It's such a complex issue. And on one hand, it's staring out into space. And on the other hand, it's people literally in a lab mixing things together and seeing what it looks like when you look at the spectra. It's so many levels of people that need to be involved. And all this makes me think, I just wish we had multiple JWSTs so we could get looks at all these worlds. I'm really glad that you guys got the opportunity to do this kind of observing because, I mean, you said it, it's difficult to get time on a telescope like JWST, but it gets more and more complicated every second that goes by because there's so many targets that deserve this kind of, unique look at.
Yeah, and I would say that since JWST has been so amazing for many scientific purposes, the oversubscription rate is constantly increasing every year. So more and more proposals for essentially like the same amount of observing time. And so it just gets more and more competitive over time. And I'm very lucky that I PI'd a program as a grad student. I think only 8% of PIs in cycle 1 were grad students. So it was just right place, right time, but also like it was a really cool idea. And I'm really happy of the team. We originally thought, oh, we're just going to look at these exoplanets. We're just going to look at their atmospheres. When we discovered this infrared excess, which is indicative of, material around the inner planet, none of us are disk experts. We always are like, oh, planet and then star, and then sometimes star has a disk around it as well. But trying to figure out, okay, well, all we have are atmosphere experts here. We need to go talk to a disk expert. And so I brought in Christine Chen and her grad student, who was a first-year grad student at the time, who is, I think, 5th author on this paper, or 4th author on the paper, to look at the spectra. And they're the ones who found that 9 to 11 little bump there. And they're the ones who told me, no, that's olivine 1,000%. We've seen that in disks around actively forming stars. And if it weren't for this multidisciplinary approach with building the team and with the research itself, we would never have found that. And so that was a really awesome opportunity as an early career student to work with more early career people and really drive this home. The first 5 authors are all early career people doing amazing research, but they are from a wide variety of little niches in this field.
It's always so good to hear that. I mean, I remember the days where it was hard to get your name on a paper unless you were a top level professor or something. And then way down the list would be the people that did the actual work, right? We're now finally in an age where not only are early career people getting their names at the front of papers, but say you're a random person that likes to do citizen science and you help discover something about one of these worlds, they'll put your name on the paper as well. So people are finally getting the credit for the work that they did. And I think it's just so well deserved. And it's a nice turn. It's a nice change. So you said that basically there's no way for us to figure out kind of, at least at this point with our current technology, what's creating this disk around 1B. And now we know more about what's going on with these clouds and 1C. But since it's so hard to get JWST time, do you think there's going to be any follow-up observations on the system anytime soon? Or are you guys pivoting to a new cool star system that you want to learn more about?
So Actually, there is a Cycle 4 program that's being PI'd by a collaborator of mine who will be using the MIRI MRS to look at YSES-1b. So that would be the inner planet, to look at emission lines and hopefully looking for dust features in the circumplanetary disk. So we have a high SNR detection, but we used a lower resolution instrument. So we're really only seeing the shape, but they're going to go back in and look at it for a pretty long time, I think 12 hours, and try to see if they can see individual lines from molecules that are going to be in the disk itself, to try and figure out what's going on in the disk and what the disk-planet interaction is. I am on that program and will be working on that data set, which I'm really excited about. And I have to look at the numbers to see if C will be detectable, since both are going to be in the field of view, regardless if you're looking at one or the other. C with the MRS, though, at that wavelength range, you would probably, in order to get a really nice full silicate feature, you would need to stare at it for like 24 hours. So we'll see, but at least YSES-1b for sure is going to be followed up and observed.
Well, thank you for helping us learn more about this system. I'm going to be putting a bunch of images from your paper along with the actual direct imaging of this system. And I just got to say, I said a little bit about this, that I was at an exoplanet event shortly after I learned more about this, but I was really glad that I had already kind of looked into your paper, because I think it was something like 3 other people giving talks at that exoplanet exposition literally were showing some of the images of the system and some of the results from this. So, I mean, it is such a cool thing that we can learn more about these systems, and it feels like a new beginning of really beginning to study these worlds around sun-like stars. It's a whole new chapter in our ability to study what's out there and things that are just a little bit closer to home, at least it feels, because their star is so much like ours.
Yeah, I mean, what Kielan did with Cycle 1 JWST observations has really paved the way in understanding what NIRSpec and MIRI are both capable of doing and what we can do with our data processing techniques. And so Kielan mentioned this program that will be looking at the YSES-1 system again in longer wavelengths, but we also have a number of programs that are now utilizing this technique that has been developed by Kielan and collaborators on other systems, and we're starting to look at increasing number of exoplanets in this way. So I think this is really just the beginning of getting these kind of observations and hopefully opening up a box into the world of understanding like what it is that we're looking at.
And hopefully way more surprises to come that are absolutely going to throw us for a loop and change the way we think about everything, as is tradition.
Yes.
Thank you so much for your time. And seriously, good luck with all your future research.
Thank you so much.
Thank you.
It's worth pausing for a moment to celebrate that so many of JWST's most exciting discoveries, like the one that we heard about today, are being led by early career scientists. These researchers are pushing the boundaries of what we know about the universe, often while navigating uncertain job prospects and unstable funding. We need to do what we can to invest in this next generation of scientists, because they're already delivering some of the most groundbreaking results. The current cuts to grant funding in the United States, along with the drastic cuts to NASA that are proposed by this presidential budget request, are putting all of these early career and young aspiring scientists in jeopardy. To learn more about what you can do to help, go to planetary.org/save-NASA-science. And speaking of future discoveries, we've been talking a lot about directly imaging and studying young, hot, giant planets. But what about the older, colder, smaller ones that might actually host life? For that, we're going to need a new kind of observatory. Dr. Bruce Betts, our chief scientist, joins me next for What's Up. We'll talk about the proposed Habitable Worlds Observatory and what it might do to help us directly image Earth-like planets around sun-like stars. Hey, Bruce.
Hey, Sarah.
I love that I got a chance to talk to the team behind this thing, because I remember a few years ago, and this is such a funny thing to remember just because, we're in Spaceland, but when they managed to capture a direct image of multiple worlds going around a sun-like star, it was just such a really cool image. Now to know more about these worlds, I don't know. This was just a story I was really looking forward to getting to tell more.
No, it's exciting, and as we incrementally discover more and more and get closer and closer to observing an Earth-like system, it's super exciting.
But in this case, it was a little easier. And I spoke with them a bit about this. They managed to do the actual direct imaging because the system was so young. And because these worlds were so large, they were giving off enough of this infrared light that they could take these images. But if we actually want to find worlds around sun-like stars that are more Earth-like, that's a lot more challenging. And I know we have this idea of this upcoming Habitable Worlds Observatory, but how is that designed in such a way that we would be able to actually image these small rocky worlds, even though they'd probably be a lot older and dimmer in the infrared than these ones are?
The plans they have so far, I mean, it's not defined in all sorts of ways, but really crazed technology. I mean, you look at Hubble, and then you look at JWST, and JWST is just, it's ridiculously technologically magnificent, and I'm still shocked that it works and beautifully. So they're trying to, just do something like that, but use methods to try to deal with this. So the big problem, to overstate the obvious, and you undoubtedly discussed it, is with direct imaging, is the star is so much brighter than the planet. And you can do a little bit better sometimes in the infrared because the planet tends to be radiating more in the infrared, and the star still radiating more in the infrared than the planet, but at least it's not where it's peaking in its radiation. So you pick the right wavelength, you hope. You work on blocking out the starlight. That's the super key. And you use a coronagraph, which others use, that is basically sticking something in between you and the star to block it out. But then you make them more and more precise and crazed and impressive in terms of how they do that. You also may, if you really get wild, you incorporate a separate spacecraft. Now that gets a wee bit tricky, but you can line up a giant, big disk and use it as an external thing to block the starlight. That one's going to be tough, but it conceptually works really, really well. And then you use a really big telescope, to overstate the obvious. And so you make a big beast and you use super sensitive detectors, and AI will be undoubtedly involved in more than it has been in the past in trying to optimize it. It's very challenging exercise. And as you say, they did well because when you form a planet, they end up being really, really hot for millions of years. And the Earth is still, all our planets in our solar system are still giving off heat. Some of it left over from the formation of the solar system 4.5 billion years ago, but some of it from radioactive elements doing heat. But right early on, that puppy's hot. And so that gives you more to work with when you're looking at in the infrared that's sensitive to that.
Trying to figure out how to create a sunshade or something like that could be really complex, but you might be able to help with that situation. And I was just having a conversation earlier today with some of my coworkers about kind of a spacecraft that did this same situation, but with our own star, to create an artificial eclipse so that we could actually see the sun's corona and things like that by actually putting a separate sunshade away from the telescope, which is just, it's cool technology, but really complex to do. But the fact that we're thinking about hopefully someday being able to do this is really exciting. We're going to be able to find all kinds of worlds. And I just love these direct images of other solar systems or
sure,
other star systems.
Super cool. And allow the more you can do that, the more you can also get spectra and information that gives you information about the chemical makeup of things like the atmosphere, which we can do now. But the more you can isolate that planet, the better off you're going to be in learning things like that. But we have a lot of most of the thousands of exoplanets we now know are out there have never been directly imaged, and were discovered using indirect techniques. And scientists, man, they get clever. And so we still find out things, but we will find them out much better in the future with cooler technology. And the Habitable Worlds Observatory hopefully will be part of that.
Fingers crossed if we keep fighting for it. Maybe we'll find some more of those worlds with rings around them. We're only having the capability to do this kind of science now, and it's only going to get better.
Yeah, it does that.
Yeah,
Hopefully
man.
it still does that. No, when I was a boy, actually, when I was a trained scientist, we didn't know of any exoplanets. So this has been an amazingly rapidly fast-growing field with the first ever exoplanets confirmed in the mid 90s, and now we have 5,000-6,000 confirmed and lots more possibilities.
Coming up on 6,000. I think the projection is they think we're going to cross that line in about October. Coming up on it. I think I mentioned this in the interview too. It was because I was at this exoplanet exposition and I was giving a talk there about something completely disconnected and got to hear a bunch of these talks. And people spoke about this YSES-1 system as well, which makes sense because if you're going to try to find images to show people about these worlds, it's a little more compelling to give them direct images that are really accessible for them rather than hand someone a spectra and be like, this means that there's silicon clouds on that world, right? So thankfully this story had both. What's our random space fact this week?
It's a not so random space fact. I wanted to honor astronaut Jim Lovell, who passed away in the last couple weeks, with a couple facts about his amazing career. He was the first astronaut to fly 4 times in space. And he was not one of the Mercury 7 because he had temporarily too much bilirubin in his blood, which is enough to throw you out.
What's bilirubin?
So, bilirubin is tied to liver function and the like. And so if you don't have enough bilirubin, I believe you get jaundice. But I am a doctor of planets, very much not a doctor of medical goodness. Anyway, but he also was the only person, he's the only person to have flown to the moon twice and not landed either time. There were 3 astronauts who went to the moon twice, and the other 2 didn't land to begin with, but then landed on a later mission. So as an unfortunate claim to fame, but he also had the most hours in space until Skylab got up there, the space station. Of all the astronauts, he had the largest accumulation. So we will miss him. He was an impressive guy.
R.I.P. Jim. Really, though, can you imagine going all the way to the moon twice and never getting to step foot on it, just orbiting about in the dark behind the moon?
Yeah, well, I'm not totally sure I can imagine going to the moon, but I tried really hard. But yeah, no, that was a bummer. Or you can say, hey, he got to be up close to the moon a couple times. Of course, the second time was a wee bit tense, but that pre-return trajectory that Apollo 13 took allowed he and his fellow astronauts to have reached the farthest distance from Earth of anyone so far.
Those astronauts were so brave. I can't wait to see what this next generation of people returning to the moon gets to do. And they'll only get to do that because of the legacy of everyone that came before. So cool.
So cool. All right, everybody, go out there and look up in the night sky and think about misbehaving cats. Thank you and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with more space science and exploration. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members who dream of distant worlds. You can join us as we work together to support the people making these amazing discoveries at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Casey Dreyer is the host of our monthly Space Policy Edition, and Matt Kaplan hosts our monthly Book Club Edition. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. My name is Sarah Al-Ahmed, the host and producer of Planetary Radio. And until next week, Ad Astra.